Hello, this is Jack Jackson. In this video we're going to be talking about the derivatives of the hyperbolic trigonometric functions. Now you may or may not have encountered hyperbolic functions before, but there are 6 basic hyperbolic trig functions, just like there are 6 basic circular trigonometric functions, the regular trig functions. And they have properties that are similar to the standard circular trigonometric functions in many ways. And in this video we're not going to get into all those details, but we will define the basic functions and talk about their derivatives at least, and maybe a few of their properties. Okay, well, first of all, they're actually defined in terms of the basic exponential function e to the x. And the hyperbolic sine of x, usually pronounced sinh of x, is defined to be e to the x minus e to the negative x, all of that divided by 2. And the hyperbolic cosine of x, or usually pronounced cosh of x, is defined to be e to the x plus e to the minus x over 2. Now, when you look at this, well, let's just look at the formulas here for just a minute. As x goes to infinity, notice that the e to the minus x part is going to go towards 0. So the further you get out to the right, the closer this function gets to just 1/2 e to the x. So it looks like an exponential growth function on the far right. Okay, and on the left, what does it look like? Well, they both look like that on the right. Both of these, whether it's plus e to the minus x or minus e to the minus x, that part gets so small that it's almost negligible, and it has sort of like an asymptote. It approaches the graph of e to the x over 2 on the far right. Of course, it's not a straight line. It's an exponential growth curve. Now, what happens on the far left? Let's look at the cosh one first. And the far left, as x goes to minus infinity, it's the e to the x term in the numerator that goes to 0. And so this looks like e to the minus x over 2, which is an exponential decay function. So on the far left, it's going to look like an exponential decay function. On the far right, it's going to look like an exponential growth function. Also notice when you plug in 0, you get 1 plus 1. Here is 2 divided by 2 is, of course, e to the 0 and e to the 0, that's 1. 1 plus 1 is 2. 2 divided by 2 is 1. So cosh of 0 is 1. So it goes through 0, 1 on the y-axis. Now, sinh of x, as you go far to the left, as x goes to negative infinity, the e to the x term in the numerator goes to 0, and this looks like the opposite of e to the minus x over 2, which is like an exponential decay curve flipped upside down. So let's take a look at what the graphs look like. Okay, so as we come down here, you can see what the graphs look like. So in blue, here we have sinh of x, and in red we have cosh of x. Now notice we also have some reference functions. Let's look at cosh first. We have, in both cases actually, we have graphed y equals e to the x divided by 2, and so we get this graph here. Okay, so it goes through 0, 1/2, and then 1 e over 2, and so forth. And you notice as you go out to the right, the graph of cosh gets very close to that. Then you do e to the minus x over 2, flips that graph over the y-axis, and it comes down like this, exponential decay. Of course, the exponential growth and decay have asymptotes. The cosh does not. It actually approaches this exponential function on one side, one on the other side. And so it looks like this. Notice that cosh of x is an even function. It is symmetric about the y-axis. If you replace x by minus x, this basically turns out to be the same. And so you get y-axis symmetry there. So at first glance, it looks maybe a little bit like a parabola or something, but it's actually a little bit different shape. It's like an exponential function on the ends. Okay, how about sinh of x? In the first quadrant, it looks pretty similar to cosh of x, at least eventually, because eventually it looks like e to the minus x, or e to the x over 2, So eventually they have a very similar shape on the far right. Okay. On the far left this time, though, it approaches this function here, which is our reference function here, which is the one down here where y is negative. And this one is going to be minus e to the minus x over 2, and we see it approaching that on the far left. This sinh of x is an odd function. If you put in e to the minus x, you get the opposite. If you put minus x in place of x, so you do sinh of minus x, sinh of the opposite of x, you get the opposite of sinh of x. So it has origin symmetry. So whatever you see here in the first quadrant, you have a rotated image of 180 degrees down here in the third quadrant. Whereas cosh was reflective symmetry, whatever you saw in the first quadrant was reflected over the y-axis to the second quadrant. Now, what would the, you've already got the result here, but what would happen here as far as the derivative? What would it look like? Well, let's look at sinh. Sinh is increasing everywhere. Okay, and so its derivative would always be positive, like cosh is. The sinh is concave down when x is negative, so the derivative would be decreasing when x is negative. And with the sinh is positive, when the x is positive, sinh is concave up, so the derivative should be increasing. So concave down here means, the original function means derivative is decreasing. Concave up in the first quadrant means the derivative is increasing. And so we have an inflection point at the origin here on sinh, and that means that its derivative is has a minimum there in this case. So the derivative of sinh turns out to be cosh. Turns out the derivative of cosh is sinh. Also, as you're going across here, we've got almost an exponential function. Exponential functions are e to the x is its own derivative, so it's not too much surprise that the derivative should look very similar there. And in fact, it's the same as cosh, which is very similar. Look at cosh. Its derivative is actually sinh. They're derivatives of each other. So notice that this function is concave up everywhere, so its derivative is increasing everywhere, which is true for sinh. The cosh is decreasing when x is negative. Okay, so that says its derivative, sinh, is negative here, third quadrant. And when x is positive, cosh is increasing, so sinh its derivative is positive there. So it turns out these are actually derivatives of each other, and of course we can do the derivative by just switching to the e's. Okay, and so here are the two functions just graphed together. The cosh is in red and the blue is sinh, and they're, like I said, the derivatives of each other. So let's actually work that out. Here are the steps here, and it's not too hard. All you have to do is to change to e's and work it out that way. So sinh of x by definition is e to the x minus e to the negative x over 2. I use the constant multiple rule to factor the 1/2 out here, and then I can bring it out front of the derivative sign. So it shows up right here, 1/2. Then I use the sum rule and take the derivative of each of these pieces. Well, the derivative of e to the x is just e to the x. Then I take the derivative of e to the minus x. That's like e to the u. So I get e to the u, so it's minus from here. Then you get e to the u, so it's e to the minus x. Then we have to take the derivative of the u. The derivative of minus x is negative 1. So that minus and that minus cancel, makes a plus. If I put the 1/2 back down, that's the form I had it when I said, okay, that's the definition of cosh of x. In a similar manner, we can find the derivative of cosh of x. By definition, cosh of x is e to the x plus e to the minus x over 2. And again, we can factor the 1/2. Whoa, come back here. Okay, we can factor the 1/2 out and bring it out front of the derivative sign. Now we have the derivative sums, the sum of the derivatives, very much like the last one, except this was a plus, so this is a plus, and that minus turns that plus into a minus, and then we have sinh of x. So pretty straightforward. And there are the graphs of the cosh of x is in red, sinh of x is in blue, and again the derivative of sinh is cosh, derivative of cosh is sinh. Now, like the circular trig functions, we have 6 of these basic trig functions, and they're hyperbolic trig functions, and they're similarly defined to the way the circular trig functions are defined. Come on, come back. Wow, this is jumping around on me. Okay, let's go on. So, remember that we can define all 6 of the trig functions really in terms of sine and cosine, the regular ones, and we can do a similar thing here for the hyperbolic trig functions. Okay, so again, by definition, sinh of x is defined to be e to the x minus e to the minus x over 2, and cosh of x is e to the x plus e to the minus x over 2. Okay, the hyperbolic cosecant of x is 1 over the hyperbolic sine of x. So in terms of the e's, it's actually defined as 2 over e to the x minus e to the minus x. The hyperbolic secant of x is 1 over the hyperbolic cosine of x. Remember, secant of x is the reciprocal of cosine of x, so you get a similar kind of result here, and so that's 2 over e to the x plus e to the negative x. The hyperbolic tangent of x is sinh of x over cosh of x, so when you divide these two, the over 2 part cancels, and you get e to the minus x, or e to the x minus e to the minus x over e to the x plus e to the minus x. And the hyperbolic cotangent of x is cosh over sinh, so it's just a reciprocal of hyperbolic tangent, so it's e to the x plus e to the minus x over e to the x minus e to the minus x. Now, we can find the derivatives of these other 4 by using some, we can either do it 2 ways. We can rewrite them in terms of the e's and work it out that way, or we can use some basic identities that I have written here along with some basic derivative rules. And it turns out that hyperbolic trig functions have lots of identities, just like the hyperbolic trig functions work, and many of them look very familiar. Not exactly the same. Mainly the main difference is negative signs show up in different places, but otherwise very similar to some of the other trig functions. So in particular, I'm going to prove one of these, and that's going to be the hyperbolic trigonometric version of the Pythagorean identity. So remember the basic Pythagorean identity for trigonometric functions is cosine square of x plus sine square of x equals 1. The hyperbolic analog of that is cosh square of x minus sinh square of x equals 1. So notice the plus here becomes a minus, and then the cosine becomes cosh and sine becomes sinh. Okay, so it's very similar kind of identity when you look at it. Now the way we're going to define this or derive this is we're actually going to prove it with going to the definitions. So I write cosh square of x, which of course means cosh of x quantity squared, and so that's e to the x plus e to the minus x divided by 2 and then square it. Sinh square of x of course means sinh of x and then square it, so we still have the minus from here, and then it says e to the x minus e to the minus x over 2 squared. So that's nothing but the basic definitions. Now we use some real basic algebra to square this out. So you square the numerator and denominator. Squaring the 2 in both cases becomes the denominator of 4. And when we square the top, you could use FOIL, distributive property, but we know it's the square of the first. So e to the x squared is e to the 2x using a property of exponents. Remember, power to a power, you multiply the powers. Or e to the x times e to the x, you add the powers. Either way, you get 2x. And e to the minus x squared is plus e to the minus 2x. And then for the middle term, so there's the f and the l of FOIL, and they get the o and the I, they combine. And so what you get is you can multiply these two and double it. So e to the x times e to the minus x, when you multiply those together, you add exponents, you get e to the 0, which is 1. Those are reciprocals of each other. Their product is 1, and then you get that for both the o and the I, so that adds up to 2. Similarly over here, except this is a minus in the middle, so the middle term is negative 2. Now you have a minus here, so in a common denominator, I need to distribute this negative here. So the first one stays the same, e to the 2x plus 2 plus e to the minus 2x. The second one, I distribute the negative 1, and I get subtracting e to the 2x minus 2 becomes plus 2 now. This plus becomes minus e to the minus 2x. And if you look, all the stuff with e's cancel. So this first term cancels with this fourth one, and the third one cancels with the last one. And then you're left with the two 2's, which of course adds up to 4. And of course 4 divided by 4 is 1. And we proved our result. We're going to need that particular one. But there's lots of different identities with these hyperbolic functions that I'm not going to go over in this video. Maybe sometime in the future we'll put something up for that, but not right now. And so we can now use this to find the derivatives of the other 4 hyperbolic trig functions using their definitions and a few basic derivative rules. So, for example, to get the derivative of the hyperbolic secant, we're going to rewrite in terms of cosh. Hyperbolic secant is cosh of x to the negative 1 power. Okay, so that's negative 1 cosh of x to the negative 2. That's u to the negative 1 is negative 1 u to the negative 2. Then times the derivative of the u. Derivative of cosh of x is sinh of x. And of course cosh to the negative 2 is 1 over cosh square of x. So when it's all said and done, I've got negative 1 sinh of x over cosh square of x. Now we could leave it like that in terms of sinh and cosh, which might be a good way to do it. But we can also write it this way. Take the sinh of x over one of the cosh of x's and put it over here by itself, and then take the 1 over cosh of x here. Then I've still got my minus here, and I can rewrite 1 over cosh x as the hyperbolic secant of x, and sinh x over cosh x is the hyperbolic tangent of x. Now remember, what was the derivative of secant of x? Derivative of secant of x is secant x tangent of x. What's the derivative of hyperbolic secant x? It's minus hyperbolic secant of x, hyperbolic tangent of x. So very similar. You change the hyperbolics here to hyperbolics here, but this one has a minus, whereas the other one didn't. So sometimes the minuses show up in different places. You can sort of verify that and also see what these graphs look like. The blue and below here are going to be the original function. So the hyperbolic secant is in blue. Notice it's going to be it's the reciprocal of the hyperbolic cosine, and so it's going to have asymptotes on the left and right here, and has a maximum right in the middle. Similar to kind of a bell-shaped curve that you would get maybe from a normal distribution, not exactly the same, but some similar properties. And its derivative is minus hyperbolic secant of x times hyperbolic tangent of x is the red one here. Notice some features of the graph. The hyperbolic secant is always positive. It's increasing for negatives, which means its derivative is positive for the negatives at negative x's. For positive x's, the hyperbolic secant is decreasing, so its derivative is negative, so it's down here below the x-axis. It starts out concave up, so the original is concave up, so its derivative is increasing. Then it switches to concave down for a while, so then the derivative is decreasing. And then it switches back to concave up on the original, so the derivative is increasing again. So where it switches, of course, you have inflection points in the original function, about here, and that would be a maximum here and a minimum here for the other inflection point up in the original. So that you have a max and a min, maximum and minimum, and extrema for the derivative when you have inflection points in the original function. So very, very similar. Okay, and of course if you have asymptotes here, a horizontal asymptote, then the derivative is going to have an asymptote of 0, and they're both asymptotes of 0 on both the left and right. In a very similar manner, you see the hyperbolic secant of x is the derivative of the hyperbolic tangent of x to the negative 1 power. Again, I could do do a substitution, say w equals sinh of x. We got the derivative of w -1, so that's -1 w to the -2 times the derivative of w. Derivative of sinh is cosh. Of course, this is -1 sinh to the -2, so that's minus, because we got the cosh of x here in the numerator, and this becomes sinh of x squared in the denominator. Again, we could leave it like that. Might be a good way to write it. But another way to write it would be to split it up. Very similar manner than I did over here. Cosh over sinh here, and then 1 over sinh here. 1 over sinh is hyperbolic cosecant. This part right here is hyperbolic cotangent, and you get a minus. So remember that the derivative of hyperbolic cosecant, or regular cosecant of x, is minus cosecant of x, cotangent of x, and so this one, notice you just switch hyperbolics to hyperbolics from the circular one, and it works out the same. You can see the graphs here. Then blue is the hyperbolic cosecant of x. Notice it has asymptotes of the x and y axes, so it looks a lot like maybe 1 over x as far as the basic shape goes there. And so its derivative, well, looks a lot like -1 over x squared. It's down here as far as its basic shape, and so that's what we would expect. Okay, a couple more here. The derivative of the hyperbolic tangent of x. Well, use our identity to rewrite hyperbolic tangent of x as sinh of x over cosh of x. And now we have a quotient, so we use the quotient rule. A lot like what we did when we took the derivative of tangent of x. We wrote it as sine of x over cosine of x and applied the quotient rule. So it's the bottom times derivative of the top minus the top times derivative of the bottom over the bottom square. Derivative of sinh is cosh, derivative of cosh is sinh. Here we have 2 sinh multiplied together, that's sinh square of x. Here we have 2 coshes multiplied together, that's cosh squared of x. Now remember our identity we proved earlier. I told you we would need it. Cosh of x, cosh square of x minus sinh square of x is 1, and 1 over cosh square of x is the hyperbolic secant of x. Now remember the derivative of tangent of x was secant square of x. The derivative of hyperbolic tangent is the hyperbolic secant square of x. So very similar. Again, in blue you have the hyperbolic tangent of x. There it is. And you see its derivative in red there. Notice that the hyperbolic tangent is increasing the whole way. So its derivative is always positive. When x is negative, the hyperbolic tangent is increasing, so the derivative is well, it's increasing the whole way. So the derivative is always positive. In the negative x's, the original function is concave up, so the derivative is increasing. When x is positive, the original function is concave down, so the derivative is decreasing. And we have a maximum for the derivative right there at x equals 0, which is exactly where the original has an inflection point. So the second derivative would be 0 when x equals 0. Very similarly, the derivative of coth, or hyperbolic cosine, hyperbolic cotangent, there we go, hyperbolic cotangent of x, is hyperbolic cosine of x over hyperbolic sine of x, cosh over sinh. So again, we can use the quotient rule. So we just used basically our defining identity there, and then our cosine, our quotient rule. Sinh of x times derivative of cosh of x minus cosh, got an extra h there, cosh of x over times sinh of x. So let's see what we got here. That's the bottom times derivative of the top minus the top times derivative of the bottom over the bottom square. That's the quotient rule. Derivative of cosh is sinh, derivative of sinh is cosh, so we get cosh square here, we get sinh square here. Again, sinh square minus cosh square of the same input, x, is -1. And 1 over sinh of x is hyperbolic cosecant of x, and of course we got that squared, so it's the opposite of hyperbolic cosecant of x squared. Remember, the derivative of cotangent of x is the opposite of cosecant square of x. So here we just ended up changing, just sticking the h's in there in the way it looks in the formula. Of course, the graphs don't look anything at all like their circular counterparts. Here is the graph of the hyperbolic cotangent of x. Okay, and the derivative is minus cosecant square of x, which is in red. Okay, so we have the hyperbolic trig functions, basic definitions, which are given by this thing. The actual definitions are in terms of the e's, and the trig function and the reciprocal identities and quotient identities here are other ways of writing them. We've seen the graphs of them all, and we found the derivatives of all of them. And just to review, derivative of sinh is cosh, cosh is sinh. Let's see if I've got well, I have a summary right down here. Here we go, somewhere. Okay, here's a summary, and let's go over that real fast, of the derivatives of the hyperbolic trig function. So going over those one more time. Derivative of sinh is cosh, derivative of cosh is sinh. Derivative of the hyperbolic tangent of u is the hyperbolic secant of u squared times the derivative of u. Notice here I've incorporated the chain rule as well. Suppose we've done a substitution. Derivative of hyperbolic cotangent of u is minus hyperbolic cosecant square of u du. And the derivative of the hyperbolic secant of u is minus hyperbolic secant of u, hyperbolic tangent of u times the derivative of u. Derivative of hyperbolic cosecant of u is minus hyperbolic cosecant of u times hyperbolic cotangent of u times the derivative of the u. And so there we have the derivatives of the hyperbolic trig functions.